So, we've got 4 lessons. Hang on, 4 lessons until the exam. I forgot to sort of start yesterday's lesson with, obviously, we've had to change the program. They bumped the exams back into weeks 7 and 8. So if we look at where we are next week, obviously I taught this in a different order, okay? So we're doing dosimetry today. We've already done those. Nuclear power stations, management of fuel, that's easy. The test is Wednesday. We do electrical physics. There is a prac in week 5. There's no validation. You just hand it in a week from the day that we do it. We get to circuits, parallel combination circuits. Then you've got the mid-year exam, okay? This has been updated. There may be a SIS test in week 4. Because the exams all got shifted back, week 4 was a non-assessment week, and now there's a vacant assessment period. So I'm fighting for the SIS test to be placed in week 4. As soon as I know, I will let you guys know. And the SIS test is just your basic sig figs, precision, error, accuracy, combining uncertainties, things like that. Yes?
Will the circuits be on the exam?
Absolutely. So the assessment outline has also changed to say that the mid-year exam will cover all content up to and including week 6. Okay? So wherever basically in the exam, there'll be combination, parallel and series circuits. Yes?
Can you scroll up to show the next test?
Yep. There may be a SIS test in week 4. Yes? Oh, no. You've wasted your... Yep. Vidler. No. Okay, cool. Sam?
Okay, I remember my question. Yeah, quiet. What is this chapter 5 point something? Which exact textbook is that?
That's the Pearson Science. Okay, yes.
In the SIS test, do we need to learn anything else?
No, it's all express this answer to the correct sig figs, express this in scientific notation, determine the absolute uncertainty of this measurement, blah, blah, blah. Yes?
Will those SIS tests be like based on electrical physics?
No, completely random. Adding numbers, sets of numbers, precision, error, how close is that value to that value? Don't worry about it.
Did we already do one?
No, that was the validation test of thermo. Last question, Kovacs. Absolutely, yes. Oh, you'd have to check.
Wait, is it a new test or a moved test?
It's a moved test. So it used to be in week 8, but then the old pesty exams just went stomp and stole my assessment period. So I've said, well, give it back to me in the shadow that you've left. The first SIS test is 4%. Okay. All right, guys, we need to get going. Oh, hello, Margaret Stewart. Wait, what was that? ATAR exam science data. Oh, Facebook. Hello. Still screen capturing. Right. Let's get going, gents. Our new booklet, please have a look. Dosimetry. Now, this is the measure of the energy that is absorbed by humans and its physiological effects that it has on us, human beings. Okay? So, we should have knowledge that radioactive emitted particles, boys, they are ionizing, they do knock electrons off atoms, they cause molecules to become ions.
I got the wrong one for myself.
Somehow.
So close to just restarting the screen capture. And so if you can be blasted with radioactive particles, eventually they're going to do so much ionizing that it damages your cells. Your cells will attempt to repair themselves, and then the more damage, the harder it is for the body to repair itself. There are 2 different equations that we need to learn. And the first is the absorbed dose. It's very easy. It's simply energy per unit mass. So could we just write in this equation here, absorbed dose is energy per mass. The units, well, it's joules per kilogram, but this is a derived unit called the Gray. Okay? So there it is there, named after a doctor. Okay, so a derived unit. Just we need to remember SI units. So we need to have energy in joules and we need to have mass in kilograms. So for example, this is one of the easiest equations you'll find. Okay, we have a mass of tissue exposed to 1.2 joules of alpha radiation. So your absorbed dose, well, first off, we got to do a little side mission. So your mass has to be converted. All right, please remember, this is now a 4-mark question instead of a 3-mark question because now there's going to be 1 mark assigned to showing your conversion to kilograms. Okay, so we'll go 1.20 joules divided by 0.15, and that is 8.00 gray. Okay, fairly simple. You can have the unit prefixes. You can have milligray, microgray, centigray. You can have a prefix in front. Yes?
Do we have to show, when we're doing the mass thing, can we just write off the side mass is equal to 0.150 kilograms?
No, because you did maths in your head and that needs to be written down. So just show the conversion dividing by 100. Okay? Now, that's only half the battle because different particles will have more effect on the human body than others. And it comes down to the properties of alpha, beta, and gamma. You could give a beta particle 1.2 joules and it would go flying off with a certain kinetic energy, right? Equal to half mv squared. You could give it to the bigger, fatter, more charged alpha particle. It would go flying off with a different velocity, right? You could give it to a gamma ray. It would go traveling off at the speed of light. They each have the same energy, but the alpha particle, because it's bigger and slower and has a bigger charge, it will do more work. Sorry, I should say that. It could rip more electrons off atoms as it races through the material. I don't know if I've spoken about the analogy of racing through the classroom and smacking kids on the head. Yeah. So that's how we... Chapel, thanks. That's how I describe alpha particles. They're more ionizing. So they effectively are more damaging than a beta particle of the same kinetic energy. So now we have an equivalent dose. Okay? Short-range particles, which are highly ionizing, are going to do more damage than a beta particle that might whiz through you, or a gamma ray which might whiz through you and not damage as much atoms. So we basically just have a factor. It's just a comparison. And they said, all right, let's start off with the weakest, which is gamma rays, and your quality factor is simply how much more damaging that is our particle compared to a gamma ray.
So higher is worse for you.
Yes, absolutely. So we can see, this is, again, joule for joule. X-rays don't do as much damage. Then gamma rays do, well, the same. Slow-moving, sorry, my bad. Isn't that strange? Fast-moving beta particles do less damage than slow-moving beta particles. Think back to the analogy of the chapel. If I sprinted through with a cricket bat, I'm not going to hit as many kids. But if I walk slowly through, you're going to do more damage because you're in the vicinity of those molecules for a longer period of time. Okay? So it's a bit strange to think. The slower they are, same with... Oh no, faster... Okay. Yeah, and it gets really, really tricky. I've stolen this from a website. You know what you've got in your data sheet? Not much. In your data sheet... No, I'm serious. In your data sheet, you've got... Well, I'll write them here. I'll write alpha equals 20. Okay? Beta equals 1. Gamma equals 1. You've got slow neutrons equals 3. And fast neutrons equals 10. Okay? Now, write that down, and I'm just going to quickly confirm you have to use the values in the data sheet. So don't try and memorize everything on the left-hand side. Yep, there they are. And they are approximates. Okay? These are not... Hold on. These are not measured values. They are discrete numbers. So you do not go, I'm going to express my answer to 1 sig fig. I'm going to express my answer to 1 sig... No, they don't take part in the significant figures determination, okay? Because someone just said, around 20. But it doesn't. It does vary slightly. Yes.
Why does a fast neutron be more dense than a slow neutron?
Don't know.
Is that?
Don't know. My chapel analogy doesn't work there.
it doesn't.
No idea. Use the. Let's just put a little bracket over here. Use the. Oh, that's not a good bracket.
Is it because a fast neutron is less easily absorbed?
Well, no. So
Well,
a neutron.
you said
Hold
that
on.
a
I'm
neutron-
gonna stop you right there. Neutrons don't have a charge, so they're not ionizing,
Yeah.
but they can be captured.
Yeah.
And if an atom sitting there minding his own business gets captured, what does it do?
Good beta.
Spits out a beta. Oh look, now we've got a charged particle travelling with a speed. So a neutron on its own
then
isn't
it might
going
spit
to
out gamma.
cause a damage, but if it's captured and then a beta is emitted, that will then have subsequent damage. So you've got to say that the neutron, if you're being blasted with neutrons, it's going to do damage to you. I don't know why it's 10 and 3. It could be the emission of the beta is much larger. I'm not sure. So let's get over to our equation. All right. It's very easy. You simply multiply the absorbed dose by the quality factor. Okay. So I abbreviate because I'm quite lazy. Dosage equivalent equals absorbed dose multiplied by quality factor. Okay. And it's measured in sieverts. I forgot really to say it's got this. Here's the weird thing. It's got the same dimensions. It's joules per kilo. Because all we've done is we've taken a joules per kilo and we've simply multiplied it by a number, 10, 3, 20. It's still the same units, but now it's in sieverts. Okay? Again, named after another scientist that investigated the biological effect on humans. Okay? So, let's just say, if I took those 8 gray of alpha particles, well, that's different to 8 gray of slow neutrons. So here we go, dose equivalent. So you take your 8 gray, you times it by your 20, and that's going to give 160 sieverts, or 1.60 times 10 to the 2 sieverts. And our slow neutrons, same amount of energy, but they're going to have a lesser physiological effect on our human body. Okay. Now, I've jumped straight into the questions. Let me just, yeah, we've got questions. We're going to skip the questions for a moment. I'm going to talk for another 10 minutes and then we can go back to them. Could you just write, because I didn't really go back and fix this document. It depends, I should say your dose equivalent depends on a few things. It's whether it's localized or whole body. Let me write that down. Whole body. Okay. So we're going to look at, if you get a whole body dose of 160 sieverts, you are a goner. You would be a lump of red pulp on the floor within a couple of minutes or hours. 160 is whack. But if it was localized, say to a tumor, so say we found a tumor that's somewhere in your body, and you just said, right, that little lump, 150 grams of flesh, let's give that 160 sieverts. That lump of flesh would then turn into pulp. The human being, the rest of the body, is unaffected. Okay? If we can concentrate the ionizing radioactive particles to just that tumor. Now,
Okay, chemotherapy.
yes. Well, yeah, chemotherapy, radiotherapy. Chemotherapy is the chemical drugs to reduce your immune system, and then you get blasted with radiotherapy at the same time. Quick story time. Madame Curie, what was her name? Madame
Curie.
Did she have a first name?
Probably.
Pierre Curie, French. She was Polish, married a Frenchman, Pierre Curie. Marie Curie and Pierre Curie. She was the first female to win a Nobel Prize and the first person to win 2 different Nobel Prizes in 2 different sciences. They discovered radium and polonium. There's a great story behind it. They basically got barrels and cartloads of pitch blend. Don't ask me what pitch blend is. It's a mixture of pitch with tar. Go on then. And huge piles of steaming tar, and they were able to chemically extract this brand new atom. It was a tiny little slither of silver metal, and it was incredibly radioactive. In fact, there is a unit of radioactivity called a curie. Now, a curie, which Minchin's going to Google search for me very quickly.
A pitch blend is uraninite.
Uraninite, so a mineral ore containing uranium. Yep, and that's it.
Formerly, pitch blende is a radioactive uranium-rich mineral and ore with a chemical composition that is largely uranium dioxide.
Uranium dioxide, and in there was a little bit of radium. And so a curie, just unit curie, CI. It's the activity of 1 gram of radium. Now, 1 gram of that metal is probably like less than a grain of rock, probably like a Tic Tac. A Tic Tac size little silver pellet of metal, and it is
3.7 times 10 to the 10 disintegrations or nuclear transformation.
37 gigabecquerels. So that in that tiny little pellet of silver metal that they'd managed to obtain, it was decaying 37 billion emissions of alpha particles per second. Incredibly radioactive. They didn't realize at the time. But they noticed that if you place this metal pellet into a vial of water, the temperature of the water would increase, and it would bring it to boil. And they're like, holy crap, we've discovered this new sort of source of radioactivity. They later also extracted radium. They called it radium because it was emitting these radio wave form of energy. They then discovered polonium, so she was very patriotic and named the newly discovered metal element after her home country. They had no idea the amount of radioactivity. Pierre, they began experimenting with this metal. What he did is he took a little pellet of radium and he placed it on his skin and he put it under a bandage, like a Band-Aid, and he just left it there for a day. And then he took it off, and underneath was this hard, calloused lump of grey skin. It had basically just killed all of the skin. And this is back in 1920. When did Marie Curie discover radium? Now, he wrote in his book, he goes, this is interesting. Maybe we could use this new form of energy to maybe kill 1898. Thank you. Maybe less 20. Maybe we could use this new form of energy to kill cancerous tumours. So he was thinking about using this energy the right way. Marie Curie died of blood cancer. No biggie there. What's the word I'm trying to say? No surprise there, because they were dealing with such high dosages that it basically killed her. It killed all of her white blood cells, and she died of a blood cancer, I believe. Does anyone want to have a guess how Pierre Curie died?
Radiation poisoning?
No. He was crossing a street in France and tripped over, and a horse and carriage went over his head. Killed him, dead in the street. But pretty sure he would have also been riddled with cancer. Apologies here, I'm being very insincere. It's not very nice. There is in a museum in Europe, again, I exaggerate, I don't know where it is, but I've read the story. In a museum in Europe, you can actually read Madame Curie's scientific journals, but they are still so highly radioactive, they're stored in a big lead-lined safe, right? And if you want to go in and look at them, you've got to obviously put on your gloves and your masks, and you can go in and you can only look at them for around 15 minutes because you've then gotten a dosage so high that you have to close it and put it away because it's still highly radioactive. The Geiger counters there going off the Richter. Yes.
How does she survive for so long?
Well, so here's the thing. It's localized or whole body. The next thing is the duration of the exposure. So, duration.
Like, Sam, this is back
Could
in
be
like
biting.
1898. I can survive.
Yes, please. So, I should say it also, obviously it depends on the energy, depends on the mass, which is really, that's the next thing. A big, fat, healthy person, if they get exposed to radiation because they're 100 kilos compared to a small child, they're going to be, they've got a smaller mass, they're going to get a higher absorbed dosage. It's also the health of the person. The ability of the person's body to fight off any infections. The white blood cells go to try and kill things. So here's where should we go from here? So we spoke about Madame, we've got the Curie, lots of contamination. They'd had no idea at the time. And the problem is, you cannot really do tests on humans or even small mammals because it's cruel now. Really,
Now these dang human
the only way you can look at the effects is to look at accidents or contaminations that have occurred. Places like Chernobyl, the firefighters that went racing in. Places like Fukushima, 3 Mile Island, and World War II. You can sort of try to estimate how much energy did a person experience, what was the radiation, what was their dose equivalent, and what was the effect on them, okay? So there's no labs out there giving people a 5 sievert dose and watching them slowly die over days, okay? So here is a radiation, so single dose, if this was, I think, let me just check my tables, hang on.
So is there a
Immediate, hang on, dose equivalent, and then
unit for like energy per kilogram per second?
Like power, but radiation.
Yeah, that's what I was thinking.
millirads per second. Yeah, there are things like that. And then you multiply it by time, and then you've got millirads. So you just multiply that rate by time, and then you're back to the energy. Guys, apologies for this poorly formatted table. Immediate effects, have a look. Adults, so we're assuming 60 to 80 odd kilos, the whole body, single exposure. So just whoop, you've just been blasted with radiation. Not over weeks or months or years like Madame Curie, but in one event, whole body dose. And then you sit back and hope that your body can try and repair itself before infection and hemorrhaging and things. So let's go to 0.1 sievert dose. No observable effects. You wouldn't notice. But if you get from 0.1 to 1, you get a slight drop in your white blood cells. Now, the white blood cells, they're like the army, the soldiers that run out, or the firefighters that run out to try and put out the fire. White blood cells, if you've ever seen them, they kill themselves in order to kill the bacteria or the infection. Okay, so that's how they're martyrs for the cause. So they race around your body trying to find germs or viruses, and they basically die themselves. So if you've got a lot of germs or bacteria or viruses in your body, then your white blood cells are going to drop. White blood cells also don't last long. They don't repair. I don't think they have. No, that's red blood cells. They die very quickly, and so again, the white blood cells are in you. If you get a blast of radiation, a lot of them are going to fall over in the immediate exposure, okay? So straight away, boom, you've just been blasted. You've just lost half of your firefighters. And now fires start popping up around the town. I'm using an analogy or possibly a metaphor. And so you've lost half your firefighters, and then they go off trying to put out the fires, and if there's too much fire and all the firefighters die, boom, that's game over, okay? Now,
You're also measuring putting out fires in lives taken.
It's an analogy.
it's a metaphor. 0.35 to half a sievert. Temporary sterility. So your gametes start to take a hit. Again, they're very sensitive to ionization. So your sperm cells and your egg cells. Now, when you get to 1 to 2, This is where the red blood cells significantly drop because they don't have a nucleus, they can't repair themselves. So again, this is the next type of blood cells starts to suddenly get ripped apart and die. That's not good because if you lose your blood cells, your red blood cells, you can't oxygenate, you can't respire, respiration, different to breathing. Hair loss. No, hang on, hold on. Rarely fatal. Once you get to 2 to 5, now it's starting to break the very fine capillaries. So you probably remember your arteries go to capillaries and then they return to your heart via veins. So your capillaries are all in your lungs, in your digestive tracts, in your eyes, your nose, your mouth, your throat. They start to rupture. So that's where you get your internal
At what
hemorrhaging.
point do you go blind?
Not sure. Probably, I don't know.
Every age.
4.5. Now, LD 50/30. That is a measure of the dose that would kill 50% of the population within 30 days. Okay? Now, again, they didn't take university trials. Come and get paid for this free trial. They may have done it with small populations of mice and rabbits because they have a similar metabolism to us, and you can sort of scale it up to compare. They would have looked at certain events, Chernobyl, and there's also the Guyana incident where they estimated how many sieverts somebody received and whether they survived or not. Okay, so it's if you ever see an LD 50/50, it means 50% of the population dying within 50 days, and then you can get LD 50/10s, LD 50/30s. Every chemical, every poison has an LD 50/50. Caffeine has an LD 50/50. Okay, it's of quite a large number. You'd have to have like 10 grams of caffeine. You know, in your Monster Energy drink, you've got 100 milligrams. So that's why it says on the side of the label, you know, don't take more than 50 cans of Mother a day. Nicotine, cocaine, heroin, all of the medicines have an LD 50/50. So you need to, your toxicity, you've got to make sure that you're not killing people. So too does radiation dosages. They have an LD 50/30. Yes?
Would anything have a 51? LD 51?
Well, the further you go down, then it would be down to, 5, there would be maybe 5 or so. But again, there's no literature, there's not enough people to have if you're a healthy, strong person and you get 5 sieverts, you've got a better chance of living than a frail old lady with respiratory problems. They both get 5 sieverts, you're putting your money on him.
Yeah.
Okay? So that's why it's a population. That's why you get a distribution of people, ages, health, genetic predispositions to being able to repair themselves, immunodeficiencies, all this stuff, COVID-19, you're talking about this stuff at the moment.
300
Down here, really, you're only looking at those poor Pripyat firemen that ran into the reactor without knowing, and they were standing around the reactor core, and then, after about 5-10 minutes, if you've ever watched the Netflix doco on Chernobyl, there's some pretty violent scenes of the firefighters that ran in having no idea what they were getting themselves into. So
It's
yes.
367 milligrams per kilogram in rats.
Of what?
360 milligrams, so that's 3.6 grams per kilo.
Yeah.
So for me, times that by 70, this is caffeine.
No, 367 milligrams per kilogram for caffeine.
Well, just say I'm a 70 kilo rat. How many milligrams of caffeine do I need? Times it by 70.
Can you get caffeine, like capsule that goes?
Yes.
That's a lot.
So usually
Fine.
25.6 grams.
Yes, okay, so I could have 250 cans of Mother, and there's a 50% chance that I'd die in 30 days.
Let's say you're a girthy boy and you're
But I'm strong, I've got a good immune system. All right.
yeah, you go on.
All right, I want to talk. I'm sorry, I told you I'd only talk for 10 minutes, but you know by now that's a big fat lie, and you're not going to get any time to work on those questions. I want to quickly talk about the Guyana incident, which is another nuclear accident where people died and they were able to sort of go, all right, how much did that person get? Did they survive or not? It's a very, very sad story. It's a tragedy. It's also a comedy, but at the end, it really is a tragedy. Basically, there was this old hospital in this region of Brazil, a bit of poverty. The government wasn't running very well at the time.
You have to drink
the hospital. No, we're not talking
over
about
your entire body weight in Monster.
Thank you. Maybe one day.
When the going
There was an old hospital. It was broken down. It was decommissioned. It was all boarded up. There were security guards that were patrolling to make sure people would come in and scavenge for scrap metal because quite poor. They would go in and try and find pieces of metal that they could then go and sell at scrap yards. What happened was there was a radiotherapy clinic that had 93 grams of highly radioactive cesium chloride that contained cesium-137. It was encased in a big capsule, and basically it had this sliding aperture that they could slide up, and out would come this beam of gamma rays, and that was what they were using to treat tumours. Okay, and so you open up that aperture and you can focus the beam onto a tumour. Now it was so highly radioactive that when it was being used, it was 74 trillion decays per second. When it was stolen, it was at 50. They were able to recover this much activity. That much was left into the environment and uncovered. And by the way, there's your americium, which is 37 kilobecquerels in units of tera, 10 to the 12 decays per second. Okay, so this was just some information about it. 51 millimeters in diameter, 48 millimeters long. The activity was 800 terabecquerels per kilo, so smaller mass, less atoms. Half-life of 30 years, not very good. Okay, a dose rate from 1 meter of the source was 4.5 gray per hour. That's gamma rays, so the equivalent dose would be 4.5 sieverts per hour if you stood 1 meter from the source. Okay?
Jeez.
They don't know where it was made, but they assume it was probably made in the Oak Ridge nuclear reactor. So, the hospital was abandoned. You can read this if you want, but let's keep going. The idea was that the security guard had snuck off to the local pub to watch a game of football or soccer, and these people were able to sort of sneak into this abandoned hospital.
Why would they leave it in the hospital?
Because it was just decommissioned. The government said, right, we're closing down this hospital, you don't have a job, pack your stuff, we're not paying you after today.
Why couldn't you just sell it?
Just sits there. When things go, well, government ran versus private, it's a bit difficult. So, Roberto dos Santos and Wagner Pereira illegally entered. They partially disassembled the unit. They placed the source, which they might just have some value, scrap metal, into a wheelbarrow, and out they went. They began dismantling the equipment. Having trouble talking. That same evening, they both began to vomit. Nevertheless, they continued in their efforts. The following day, Pereira had diarrhea, dizziness. His left hand had begun to swell. He soon developed a burn. Later, he had to have his fingers amputated on that arm. On the 15th, Pereira visited a local clinic. He thought he had food poisoning. He was told, go home and rest, it's fine. Because how often do you be exposed to a pellet of cesium-137? The doctors just said, yeah, you've probably got diarrhea, food poisoning. He kept at it and he managed to free the cesium capsule from its protective coating. His forearm then required amputation. The source was then partially broken. He managed to puncture the window with a screwdriver, allowing him to see a deep blue light coming from the tiny opening. He scooped out some of the glowing substance. Thinking it was perhaps some kind of gunpowder, he tried to light it, but no, it wouldn't ignite. The thoughts are that it might be either fluorescence or a Cherenkov radiation if there was any humidity. We'll talk about Cherenkov radiation later because it's not in the course. Well, neither is this really, but It's interesting.
Just like everything else.
Hey! So,
This guy.
now here's the next problem. Contact tracing, right? That's one of the buzzwords this month. He sold the item to a nearby scrapyard. Dever Alvarez Ferreira, the owner, he noticed the blue glow, possibly supernatural. Hey, let's bring it into the house. Let's bring our family and friends around to have a look at it. Okay, that's not very good. He succeeded in freeing several rice-sized grains of the glowing material. Alves began to share it with some of his various friends. That same day, his wife began to fall ill. He eventually sold the scrap metal to a second scrapyard. Contact tracing. Ivo and his daughter. They successfully scraped out some additional dust, took it to his house a short distance away, spread some of it on the concrete floor. His six-year-old daughter later ate a sandwich. She was fascinated by the blue glow, applying it to her body, showing off some kind of crazy glow-in-the-dark dance.
Isn't eating it real bad?
That's real bad, yes. Dust from the powder fell on the sandwich she was consuming. She absorbed 1 gigabecquerel, received a total dose of 6 gray, more than a fatal dose even with treatment. Finally, someone with some sense, Gabriela Maria Ferreira, said, hang on, something's not going on here. People are dropping left, right and centre around me. It's not the dodgy sandwich making the food poisoning. So, okay, she reclaimed the items 15 days after she put... All right, let's tell somebody. She put it in a plastic bag. That was good because it prevented the powder from spreading, okay? I believe gamma rays ain't going to stop... ain't going to be stopped by a plastic bag, right?
I believe.
So,
4 feet of lead.
A foot of lead, like a meter of concrete.
Yeah.
the sources, a visiting medical physicist who just happened to have a Geiger counter, went, hang on, holy shit, and that's when they notified the authorities, okay? So, and then the news spread throughout international, national, local media. Within days, 130,000 people swarmed the hospitals thinking that they might be suffering, because they're hypochondriacs. They're like, I've got a stomach ache, or maybe I've got radiation poisoning. Of those, okay, they got 250 of them. They still had some residue on their hands and their skin. Okay, so here were the fatalities. So these were the people that did not make it. Now, remember gamma ray, so there's the absorbed dose, multiply it by 1, you get it into sieverts. So poor Liede, she got 6 sieverts. She's a young girl, small, she was a goner, okay?
She's buried in...
A fiberglass coffin lined with lead to prevent the spread, so because she still had it on her body. Like, what do? We had some jokes this morning. One of the jokes was, if you clean something, you're just making something else dirty. Yeah? So how do you decontaminate this powder? If you clean the body, you're just making something else dirty. So put her in a lead-lined coffin. Gabriella, the lady who had the actual brains to say, hang on, something's not right, she got 5.7. Israel Baptista got 4.5. Admilson got 5. These are all estimates, right? They're going, where were you near the source and how long did you stay there? So these are all obviously estimates.
They could be pretty wrong.
In Dever Ferreira, he got 7 sieverts and survived, but then became a chronic alcoholic and died of cirrhosis of the liver. So that's a secondary effect.
His entire family died. That's why you're getting
So these are the dosages. You can see the ones that required hospitalisation and then the ones that were fatal. So again, you can't say if you get 5 sieverts that you're going to die. That's why there's an LD 50-30. All right, you've got a 50% chance of dying within 30 days. Okay, so again, these poor people, they had no idea what they were getting themselves into. They thought it was possibly supernatural. They didn't just like Marie and Pierre Curie. They had no idea of all of the energy that their cells were absorbing. Okay, so
is the LD 50-50 thing? Is that like a continual thing, like a half-life? So is it every 50 days you have another 50% chance of dying?
No, I'm not sure about that. If you haven't died,
Like sequential.
it's either okay. I would say either you do die within 30 days or you don't, and so 50% of that population. So I'm not, yeah, you're right. After that, you could still probably die, but technically you didn't die within the first 30. So that's what determines the LD 50-30. Guys, we have 10 minutes left.
Or 5 minutes left.
10 minutes
So
left.
we have to do 5 for
That's why I said you got 10 minutes left. Can you guys work through these questions, please?
What's the time?
Please and thank you. Don't worry about the time. Get these questions done.
Oh, we have 3 minutes.
Get them done. Because, yes, I'm going to say you can start over the weekend downloading the past nuclear tests because we're pretty much one lesson left to cover to finish the course. Maybe two lessons left.
These formulas like DEG and stuff, is that all on
The question was, are they on the data sheet?
that one?
He really could have found out himself, but let's have a look. Yes, they are. There is our nuclear. There they are. So that's it. And then the quality factor is somewhere else in the data sheet. Okay. So 2 equations. One table with quality factors. Could you please get as many questions as possible in the next few minutes, please?
So how would you do the first question? There's no grades, it's an SB.
Yeah, okay, so go. Oh, geez. You could find out the absorbed dose because we are told that it's X-rays. So X-rays have a quality factor of 1. So divide that by 1. The absorbed dose is also
That's not on the data sheets.
Yes, it is.
No, X-rays on.
Yes, it is. Calling me a liar? Tell him, Manus.
X-rays on.
X-rays are on the data sheet. Oh crap, they're not. Ah!
A legal question. Ranking social distance.
All right, so QF equals 1.
Wait, so is the equivalent dose the dose equivalent or the absorbed dose?
Dose equivalent or equivalent dose, same word. So your absorbed dose is 0.4 milligray, okay? Remember, we'll try and catch out some students by using the metric prefixes. Okay? So there'll always be a few students that just go 0.4 sieverts instead of 0.4 millisieverts. We'll let all of these students get to their lockers before
Because that's the reason you wanted something.
Wait. Oh, because.
So now you've got the absorbed dose. Who was asking the question? Matthew? Yeah. So now you've got the absorbed dose, you've got the mass, rearrange the equation for energy. So yeah, that was a nasty question to start with.
Grades.
Whatever that is. 0.48. Oh, what a banger of a question. I think I've only added these questions this year. Question 1 is probably one of the harder questions. It should be at the back. But what have we got? We've got 50 times 10 to the 3 times 1.6 times 10 to the negative 19. That's energy per N in joules.
How have you done?
Because I know that 1 EV is that.
Right, yeah.
All right. Gosh.
Oh, 10 to the 3.
What a nasty question. 50,000.
What is N?
So what's N?
Well, that's energy per X-ray. So now we've got 8 point.
0.004 over
Is that the
1.6.
equation we should know? Yeah, but N.
What if I just wrote E per X-ray?
That works.
Okay. So this is where dimensional analysis comes in. We've got joules per event, and we've got joules. If I divided that by that, then we would be left with N. So I reckon we need the energy divided by the rate. So I'm going to go 0.48 times 10 to the negative 3 divided by 8 times 10 to the negative 15, and that would give me the number of X-rays.
So there should be 2 zeros.
Yes.
Oh, yeah.
6 by 10 to the 10. Note to self, I'll put question 1 at the end. If the ionizing radiation had been an alpha particle,
So why?
That's
Sorry,
50,
what a
50
copyright
times 10 to the
symbol
negative
All the
3.
questions are related. All of them.
no, because it's KEV. So how about I do an old highlightery of him?
We need to add.
Okay. I know, right? There's a lot of stuff going on.
Dear Lord, sir, the third question has been butchered.
What, C?
Yeah.
Yeah, I'll put that to a Adobe formatting issue there.
How nice.
And also,
It's all nice.
reionizing.
Reionizing?
This question's together.
If the three-ionizing radiation.
I'm scared.
Oh, you
Oh,
can't
no,
say
you have a box there, but we have a 3.
Do you?
Yeah.
Oh, lucky you.
I'm not glad to do
So what's the point?
I need to review all the half-lives.
So should it be 16?
Well, there's a factor of 20. 16 where? Where are we looking, Emil?
Like 10 to the power 16 or 10.
No. I did 0.48 times 10 to the negative 3.
Oh, it's negative.
It is. Don't know. You forgot the milli. I'll do this boy here.
What's going on in question 1B?
I know. Don't worry.
Don't
worry. Go to question 2. Question 2 is nicer.
6 and 10 to 10 is nice.
So it's 310 almost.
Yeah.
No, there's still kids out at their lockers. I can't let you out into.
Oh.
So I need
It's the three.
Yeah,
No, you
I
don't.
have places to be.
No, you don't. It's been
Yes.
cancelled.
It's been.
It's been cancelled. It's not on.
The trains have not been cancelled.
Public transport. Wait, who here is getting that one school special bus to City Beach that if you miss, you're walking? You?
Oh, you've definitely
Really?
missed that.
I got a year 7 kid in my tute who, if he misses the bus, he gets in trouble. He's got to call mum and dad. They're going to drive to pick him up.
Wait, are we doing these questions still? Because it is kind of.
You don't have to go. You can hang around.
I do have to go, unfortunately. So.
All right.
Okay, maybe I'll leave it out. Mitch's out.
Oh, look at this alpha decay of radium to radon. See you later.
Does RA have?
Huh?
So should we do these for home?
So would it be 10 to the power 11 or 10 to the power 10?
I need my good old periodic
Do
table.
this for Monday, sir?
No, do it now.
So it'll be 11.
So I have test training.
It's been cancelled.
Nah,
One.
What?
actually allowed.
Yeah, it's a private lesson. Don't worry.
Oh, you in the? All right then.
You're still
It's
so
not
hard.
30 seconds. Isn't it?
Oh, so we're all state level tennis players now, are we?
No, I actually got
I
enough.
actually am. I'm 16.
Ooh, is that right? Does he play? Does he? All right, guys. Catch you all up. Download all the past nuclear tests and do them.
So wouldn't that be plus the four?
It's like 5 tests.
Yeah, do them.
So wouldn't that be? Wouldn't you then add to that the
Yeah, I haven't finished yet. I got busy insulting Vidler.
I missed a lot of the half-lives though. 86, yeah, and then you add 4 to alpha.
There we go. Boom. All right.
Is it energy release with the?
Ooh, now here we go. Gas. Radon 222. So this guy also undergoes alpha.
Why is it?
But they're much more dangerous
Why is
than
that?
those because I think radon is a gas which can be breathed.
Yeah.
So
Expected knowledge.
Which makes it much more dangerous. So you're saying it can solidify if it goes down?
we'll have a think. We will answer this. Alpha can't get past the first layer of dead skin, right?
Yeah.
But if you breathe in something and it goes into your
Yeah,
fine capillaries in your lungs, that's where alpha particle.
Couldn't you also know what each particle can appear for?
So it
No,
says
because
it's
breathing-
found in soils, right? But
I mean, like, should we know that alpha can't get past the first layer of dead skin?
it's a gap. Yeah. All right. All right. Sit down.
Would it be because, wait, sir.
Hang on.
Couldn't you also- couldn't you also-
Alpha, beta, gamma. Properties of. Oh crap! Where are they?
It's so confusing how radium and radon work.
Yeah, that got me thinking a bit. Here, alpha. Penetrating ability very poor.
Oh, I know that. Yeah.
Yeah. So
High ionization ability.
alpha particles are not capable of penetrating through a sheet of paper or beyond the skin of a person.
Aren't they more damaging?
So
if they get through?
the only way that alpha can damage you is if you inhale it as a dust or a gas.
But then it's really bad.
Then that's bad.
Because
Because then it gets stuck to the mucous membrane of your lungs and it yoinks them. It bonks them.
Because isn't once you ingest alpha, isn't it much worse than?
Absolutely.
So
So
when you're just chilling naturally, if your respiratory system is shut, gamma is the most dangerous.
say that again. When
If
you're
you're just chilling without breathing,
Mhm.
gamma is the most dangerous.
gamma and beta, because gamma might travel all the way through you. So it depends on their energies.
And gamma isn't a like.
Because remember, gamma has a lower quality factor. Gamma is just a photon of
Yes.
light.
So what are the ranks
But
of
beta is an
penetration
electron.
ability of each particle? Right.
So gamma and X-ray and slow betas are all one.
This is
Sorry,
penetration ability.
This is a quality
What
factor.
about penetration?
Oh,
Gamma.
we'll have a look at that. It's gamma goes the furthest, then beta less, then alpha less.
We didn't know
Yes.
Yeah.
It's like from like
I would familiarise yourself with this table here.
that. No, I mean, like,
Approximate.
we need to know those materials we can pass.
Yeah, so I would say you should need to know for shielding. So here's the thing: if there is gamma being emitted, then we have to shield it with inches of lead or a metre of concrete. So that's why around the nuclear reactor, got to be a metre of concrete. When I brought in a thin little, did you see the cloud chamber video?
yeah, sure. We watched it.
Lie. Correct.
Cloud chamber.
It was like that thing.
The cloud chamber. I filmed it in week 10 when you guys weren't
It
here.
was little lights going.
Yeah.
Yes.
In
I
that,
watched that.
when I placed that pellet, it was lead 210, which only emits beta particles, and they're so weak that they could be shielded by a couple of mil of plastic.
You think.
But you
No,
can't.
that,
But then 10 years later.
so when it's sitting there, it can be stopped by a couple of mil of plastic.
In primary school, we all said it's paper, aluminium, lead. It's like what stops the three.
Who was teaching you in primary
Yeah,
school?
what the hell?
Yeah,
You're doing HR physics in
PIAC. Did you do PIAC?
Okay.
PIAC was on radiation. Yeah.
Oh, I saw you on the Enigma ad for.
Yeah. Boys and sort of
That was a script, brother.
You were reading that off a teleprompter
I was,
really
yeah.
well. The Enigma program has stimulated and has really challenged me
Yeah, Dr. Allen,
to
I
push
agree.
myself
I don't
and
even do anything.
solve
I did
problems.
not take
and-
an Enigma. Oh man. What's the coding one with Khan?
And then they like started posting stuff, so now everyone's looking at the channel and I'm just there.
Well, I don't know how I saw it.
I'm not the thumbnail. It's like
I saw it a couple of weeks ago, and I'm like, "That's Manus from like 3 years ago, isn't it?" Was it 3 years?
Yeah,
4 years.
It's like, yeah. So
I don't know how I saw. Maybe I was looking at Christchurch's Vimeo. They've got like 5 Vimeo videos.
I felt a bit out of my depth with Marcus and Ben, but
You're in their shadows. See ya. Whoops. Oh.